Okay, so just a few things left that we didn't quite get through before lunch, and then we should have a good chunk of time today for work time. So they're going to start talking about this thing called the natural base. In the natural base, that is just truly the number e. Kind of like pi is a number, e is also a number. You would see that if you are on your graphing calculator, there are two places where we have the E button. The E button that I want you to use is right here, and it's located with the natural log, but it's right above it. So if you hit second and then the natural log button, it brings up that E raised to. That's the one that we're going to use because whenever we use it, we're going to be raising it to some power. So it's called the natural base because it is a base that we're going to be raising to a power. If you want to know what it is, I raise it to the first power. It is 2.718281828, and it continues on forever after that. Okay, so it's just a number. I should show you this. If you use somewhere on the right, the divide. If I do the second and then the divide, it does just give you E, but then you have to specifically say raise it to some power if you wanted to do that. But it does show you that, yep, that is the correct value of E. Okay. So they are going to ask us here to describe some transformations. So I've got g of x, h of x, k of x. You might not need to write this example down. I'm just going to talk through it. Just because they're using E does not mean it's any different than this one here. I'm just comparing it to a different equation. So when I compare this one, if I'm starting here and I want to end up here, I see the only thing different is that 2 in the exponent. Anything inside of the function is horizontal something. Remember, every horizontal something does the opposite of what I think. So even though I'm multiplying by 2, this is going to be a horizontal shrink by 1/2. Okay, so kind of like if that other one, when we were subtracting one, we said it went to the right one. Here, I take that, I take its reciprocal, and I'm going to say, well, the reciprocal of 2 is 1/2, so that's a horizontal shrink by 1/2. This one, we've got a negative inside. Anything inside, we said, is a horizontal thing, so that's going to be a reflection over my y-axis. And then just like that last one, if I've got a times me by 3 up front, that's going to be a vertical stretch of 3. Okay. There is one other thing that's in here, or in this section, that I wanted to touch base on. That was on this. So that's on logistic functions. So logistic functions, these were one of our 12 basic functions. If you remember when we had our logistic functions, or when we had our 12 basic functions. Logistic functions, back in March, maybe even back in February, when COVID first came out, and they were making predictions about how long until we would reach our maximum, and then we would say that it would slowly die off if people did everything that they asked us to do. They were using logistic functions to actually calculate this. Okay? If you were, which you weren't, if you were in my pre-calc class last spring when this all hit, we actually looked at all of the numbers and we made a prediction, and we were supposed to be done with COVID by the end of May, but then people weren't social distancing and wearing their mask, which that obviously affects any situation. But what logistic functions do is they take on the look of an exponential graph right away. So they're going to start out and there's going to be a drastic where it is increasing really quickly. But then for COVID, we would have reached what's called a herd immunity. It's going to kind of flatten off and say that's all that's going to happen here. So a logistic function, here's our two basic logistic functions. We typically use this one. We are using these only for logistic growth functions. So you don't have to worry if there's ever a logistic decay. But a logistic function is going to have two asymptotes, two horizontal asymptotes, I should say. And I'm going to draw a graph of it right here. So it'll have two horizontal asymptotes. those two horizontal asymptotes are going to be at y equals 0, because if I'm talking about populations, it would not make sense to have a negative population, as well as y equals this top number right here. That top number right there is sometimes referred to as our maximum sustainable population. That's what or they sometimes also refer to that as our limit to growth. That's the most that could happen. Okay? So if I'm sketching a graph of one of these, I'm going to draw an asymptote at y equals 0. Wherever our c value is, here's my c value, I'm going to have something like that. The only other thing I want to see when you do this, when you draw these graphs, oops, that's not where I wanted it, is I also want you to graph your y-intercept. To find your y-intercept, which is also known as your initial value, the reason why it's called our initial value is because that's what's happening at time 0. You're going to substitute x equals 0 into your equation. That will tell you my initial value, which is truly my y-intercept. So you're going to plot whatever that point is. And these graphs look like this. They're going to start out like an exponential growth. So it's going to start to look like exponential growth. But as I get closer and closer to that other asymptote on top, it's going to kind of flatten out. Okay, so that's what a logistic function does. These are much, much better for population predictions, because with exponential growth, it just keeps growing and growing and growing forever, and it doesn't really take into account that eventually you might run out of space, or you might run out of food or water or things like that. So we're going to try just this one, where it says graph the function, find the y-intercept and the horizontal asymptotes. So these are logistic functions. They're both going to be logistic growth functions. I'll show you how much work I need to see for ones like this, because there will be one like this on a future test or future quiz, so I want to make sure you can understand exactly what I'm looking for. For this first one, what I want to do is I'm going to find the y-intercept, and I'm going to find the horizontal asymptotes, and then I'm going to draw my graph. Okay. To find my y-intercept, I just have to put 0 into that function and simplify. When I simplify that, if I take 0.7 to the 0 power, anything you told me earlier today, anything to the 0 power is 1. So that would really be 1 plus 3 times 1. All of this is just times 1 now instead. Well, 3 times 1 is 3. 3 plus 1 then would be 4. 8 divided by 4 would give me 2. This graph is going to cross my y-axis at 2. It has an initial value of 2. Do not get confused with our exponential equations. In our exponential equations, our a was our initial value. This is not my initial value, even though it kind of looks like it could be. And so you have to actually plug in 0. My horizontal asymptotes are 0 and 8, whatever that top number is there. So if I need to draw this graph, I'm going to draw an asymptote at 0. I'm going to draw another asymptote up here at 8. I'm going to plot a point right here at 2. And then I'm going to draw my best, oops, that should be a flat line right there, logistic function that I can. Okay. Same type of thing if I try this last one right here. If I try this last one right here, my y-intercept. Now they do have that e, but that doesn't matter. I'm going to put 0 in. -3 times 0 would be 0. E to the 0 is still just 1. Anything to the 0 power is 1. So I really have in the denominator 1 plus 2 times 1. Well, 2 times 1 is 2, so that would be 1 plus 2, which would be 3. So my y-intercept is 20/3. You want to write that as a decimal, that's 6.2, or not 2, 6 2/3. So 6.6 repeating. My horizontal asymptotes are going to be at 0 and 20. Then I can draw my graph. I'm going to go by 5s. So I have a horizontal asymptote at 20, another one down here at 0, and 6 2/3 is probably about right there. And there's my logistic function. Okay, so I don't need a ton of points when you're drawing those logistic graphs. Just try your best for those. Okay. Yeah, I think that is everything for our notes for today. So I'm going to end this recording. Friends, if you joined us a little late,